Welcome to the deep dive. Today, we're tackling something really fundamental if you're working with platforms like OpenShift. We're digging into what it actually means for your application to be, well, a good citizen in that kind of environment. Because it's definitely not just about getting your code to run, right? It's making it cooperate.
Yeah, that's a great way to put it, making it cooperate.
So our mission here is to really parse this document we have on OpenShift best practices. We want to pull out the key stuff on how to design apps that genuinely work with the platform's features, scaling, orchestration, security.
Yeah.
So you're not constantly fighting the system.
Exactly right. OpenShift, I mean, it's Kubernetes underneath, but it's an opinionated platform. It expects certain things. And being a good citizen, well, it's pretty much essential if you want those benefits.
Yeah.
It really is the difference between an app that's a constant headache, always needing restarts, and one that the platform can actually manage, scale, and even heal reliably by itself.
Okay, so to make this manageable, we're going to structure this chat kind of like you'd think about your apps. We'll kick off with what seems like the easiest type, stateless web services. Then we'll move into batch jobs. And finally, we'll get into those trickier stateful applications. And after covering the specifics for each, we'll wrap it up with some general best practices that really apply to anything you run on OpenShift. Sound good?
Sounds like a plan. A guided tour.
Perfect. Right then, let's jump in with stateless web services. These are probably the bread and butter for most people, yeah? APIs, microservices, maybe simple web front ends.
Definitely the most common starting point.
So what's the absolute core thing that makes an app stateless? And why is that so helpful for OpenShift?
Okay, so the key idea is that the running application process itself doesn't hold on to any unique client data or session state within the container. Think of a basic web request handler. It gets the request, does its thing, sends the response back, and then it forgets about it. Any state it needs, like user session info, application data that gets pushed out to somewhere external, a database, a cache, maybe a message queue.
So the container itself is just like
Right.
a temporary worker. It doesn't hold the important stuff.
Exactly. Ephemeral and replaceable, that's the magic word. And that's why platforms like OpenShift love them, because there's no critical state inside. Any single pod can just disappear and be replaced. If a pod crashes or the node it's on has issues or OpenShift wants to move it, fine. Just start a new identical one. It doesn't matter which pod gets the next request because they all look the same, and pull state from those external systems.
Which makes scaling out super easy, I guess.
Bingo. Horizontal scaling becomes trivial. Just run more identical copies. And you get high availability built in because if one pod fails, the others running behind the OpenShift service or route just pick up the traffic. No interruption.
Okay, that design makes perfect sense. But getting that stateless app into OpenShift, it's more than just Docker run, right? What are the absolute must-have configurations, the
Yeah.
things you have to get right?
Oh, absolutely essential. If you skip these, you're really missing the point and probably causing yourself pain down the line. First up, health probes. You need both liveness and readiness probes. Seriously, define them.
Okay, probes. Liveness, readiness, what's the difference there? Why both?
Right, so a liveness probe basically asks the container, are you still alive and functioning? Maybe the process is running, but it's stuck in a loop or deadlocked. If the liveness probe fails repeatedly, OpenShift says, okay, this one's broken, and it restarts the container. Tries to fix it. A readiness probe is different. It asks, are you actually ready to receive traffic right now? Maybe the app just started and it's still, I don't know, loading configuration, warming up a cache, connecting to the database. Until that readiness probe passes, OpenShift holds back. It won't send any user traffic to that specific pod.
Got it. So liveness is, are you okay? And readiness is more like, are you open for business yet?
Perfectly put. And getting traffic only when you're truly ready is fundamental for doing zero downtime deployments and effective scaling. Second essential, resource requests and limits. You really have to tell OpenShift how much CPU and memory your container expects to need, that's the request, and also the maximum it should ever be allowed to use, that's the limit.
Why can't a scheduler just figure that out? Isn't it smart?
It's smart, but it's not psychic. The request tells the scheduler how much resource to sort of reserve on a node. It guarantees your pod has enough to run its basic functions without fighting other pods for scraps. Without requests, the scheduler might cram too many pods onto one node and then everyone suffers. And limits are your safety valve. They stop one runaway app, maybe with a memory leak or a crazy CPU loop, from hogging all the resources on the node and killing everything else.
Makes sense. Protect the neighbors.
Exactly. One quick tip from the source, though. Be a bit careful with very strict CPU limits. If your app sometimes needs short bursts of CPU, A tight limit can actually throttle it and slow it down unexpectedly. Often it's better to set requests based on normal use, maybe give limits a bit more headroom, or just rely on scaling out more instances if you hit CPU bottlenecks.
Okay, good tip. So probes, resources.
Hmm.
What else is essential?
The third thing is really about organization and letting other tools work. Labels and annotations. Use clear, descriptive labels on your deployments, your services, your pods. Things like app.kubernetes.io name, component, version. These act like metadata tags. They let you easily find, filter, and manage your stuff in the OpenShift console or using awk commands. Super helpful. Annotations are more for tools. An annotation might tell the monitoring system, hey, scrape metrics from this pod, or signal a service mesh to inject its sidecar proxy.
Right, labels for humans and organization, annotations for machines and automation.
Pretty much, yeah.
Okay, so we've configured it, it's running, OpenShift knows when it's ready. But what happens when it needs to stop? Like during an update or if we scale down? How does a good citizen handle shutdown?
Yes, graceful shutdown. This is so important, and honestly, it gets missed surprisingly often. When OpenShift decides a pod needs to terminate, it doesn't just kill it instantly. First, it sends a signal SIG term to the main process inside the container. A well-behaved, good citizen application needs to be coded to actually catch that SIG term signal.
Okay, catches the signal
Yeah.
and does what? Just exit.
Not quite immediately. When it gets SIG term, it should first stop accepting new connections or requests. Maybe it closes its listening port or makes its readiness probe start failing. But, and this is the crucial part for, it needs to finish processing any requests it's already working on. Let them complete normally. Only after all that in-flight work is done and maybe it's cleaned up resources like database connections, then it should exit cleanly. OpenShift gives it a time limit for this, called termination grace period seconds. Default is often 30 seconds.
And if it doesn't finish in time?
Then OpenShift eventually loses patience and sends SIGKILL, that's the hammer. It forces the process to stop immediately, which could mean dropped requests, maybe half-finished transactions. Not good. So handling SIG term properly is key.
Definitely a key part of being good. Okay, what about the fun stuff? Scaling, rolling out new versions. This is where stateless is supposed to shine, right?
Absolutely. Stateless apps are perfect for horizontal scaling. Because any instance is as good as any other, you can easily set up a horizontal pod autoscaler in HPA. You tell the HPA, watch the average CPU usage, or maybe watch the request rate. If it goes above a threshold, automatically add more pods. If it drops, remove some. The platform just spins up or down those identical copies, and the service load balances across whatever's running. Simple and effective.
Nice. And updates.
That ties right into rolling deployments. This is the default way OpenShift updates things like deployments, and it's designed for zero downtime. If you have your readiness probe set up correctly, OpenShift does it smartly. It starts bringing up pods with the new version of your app. It waits for those new pods to pass their readiness checks, meaning they're ready for traffic. Only then does it start terminating the pods running the old version. It's a phased handover. You always have healthy pods serving traffic throughout the update.
Smooth. And you can add extra safety nets too.
Yeah, you can use a pod disruption budget, a PDB. This tells OpenShift, hey, even during voluntary disruptions like rolling updates or node maintenance, I need you to ensure at least X number of my pods stay available. Adds another layer of confidence.
And configuration changes. You mentioned externalizing that earlier.
All right, so for configuration changes, because you're using ConfigMaps and secrets instead of baking config into the image, updates are easier. You update the config map or secret object itself. And OpenShift can even be set up to automatically detect that change and trigger a rolling update of the pods that use it. So the new config gets picked up smoothly.
Wow, okay, that's a pretty solid checklist just for stateless apps. Build it right, configure probes and resources, handle shutdown gracefully, leverage scaling and rolling updates. What about the whole life cycle? Getting it into the cluster via CI/CD and actually seeing what it's doing observability.
Good points. For continuous delivery, you want your CI/CD pipeline, whether it's Tecton and OpenShift pipelines, Jenkins, GitLab CI, whatever, to build your container image and push it somewhere OpenShift can access. Could be the internal OpenShift registry, it could be Quay, Docker Hub, etc. Then use OpenShift's image streams. They act like a pointer to your image, and you can configure deployments to trigger automatically when a new image appears with a specific tag in the image stream.
Tags. Like myapp.latest.
Ah, no, that's the crucial bit. Immutable tagging, please. Never use .latest for anything serious, especially production. Use tags that don't change, version numbers, myapp.v1, tot2, tot3, git commit hashes, myapp.a1b2c3d, build IDs, myapp.build4f6, something unique. Why? Because latest can change underneath you. Using immutable tags guarantees that the image you tested is exactly the one you deploy. It makes rollbacks predictable, and it lets you promote the exact same image artifact from dev to staging to prod, just changing the external configuration.
Okay, immutable tags, got it. What about logs?
Logging. The absolute golden rule in containers is simple. Write your logs to standard output, stdout, and standard error. That's it. OpenShift is built to automatically collect those streams from every container and aggregate them centrally, usually using tools like Elasticsearch Fluent Kibana or Loki Promtail Grafana. Don't try to write logs to files inside the container. That storage is ephemeral. The logs disappear when the pod dies.
And make those logs easier to read.
Yes. Use structured logging if you can, outputting logs as JSON objects, for instance, and include things like a correlation ID or request ID that follows a transaction across different services. It makes searching, filtering, and debugging in your central logging system so much easier.
Makes sense. Logs sorted.
Yeah.
Metrics.
Metrics are non-negotiable for understanding performance and health. Your application should expose key operational metrics. Think request rate, error rate, latency percentiles, maybe queue sizes if you have internal queues. The standard way is to expose these in Prometheus format on an HTTP endpoint, often metrics. OpenShift's built-in monitoring, based on Prometheus, can then be configured to automatically find and scrape these metrics. You usually just need to add a couple of annotations to your deployment or service, like prometheus.io script to true and prometheus.io port, your dash metrics dash port. These metrics are gold for dashboards, for setting up alerts, and for driving things like the HPA for autoscaling.
Right. Metrics drive automation and visibility. Last one. Tracing.
And finally, tracing. Especially if you're building a system with multiple microservices talking to each other. Instrument your code using libraries compatible with OpenTelemetry or Jaeger. The idea is to propagate a unique trace ID across service calls. Each service then emits spans data about the work it did for that trace ID. OpenShift often has operators for Jaeger or other tracing backends that collect all these spans and let you visualize the entire flow of a request through your distributed system. It's incredibly powerful for understanding latency bottlenecks and debugging failures in complex environments.
Wow. Okay, that really paints a full picture. Being a good stateless citizen is definitely more involved than just containerizing. It's designing and configuring for the platform.
It really is. You get so much more out of OpenShift if you play by its rules.
All right, let's shift gears then. Not everything is a long-running service. What about tasks that just need to run, do a job, and then stop? Like generating a report overnight or a one-off data migration.
Yeah, those are your batch jobs. Very different pattern. In OpenShift, you use Kubernetes job resources for these, or if they need to run on a schedule, you use cron job resources. The platform understands these are meant to run to completion. It tracks their status, knows if they succeeded or failed, and can even handle retries automatically.
So the big difference from a service is they're supposed to terminate.
Exactly. Run to completion. That dictates the key principles. First, obviously, use the job API. Don't try to run a batch task inside a long-running deployment. Use a job or cron job object. Second, and this one's really important for jobs, design for idempotence.
Idempotence, meaning you can run it multiple times and get the same result.
Basically, yeah. Or at least, running it again won't cause harm or corrupt data. Why? Because OpenShift might automatically retry your job if the pod fails mid-run. Or, with cron jobs, there are edge cases where you might get overlapping runs if one takes too long. Your job logic needs to be robust to that. Maybe it checks if a piece of work is already done before starting it. Maybe it uses database transactions carefully. Maybe overwriting output files is safe. But you need to think about it.
So if it's processing a big file, crashes halfway and restarts, it shouldn't mess everything up.
Precisely. It should either cleanly resume or safely reprocess from the start without bad side effects. And third, just like stateless pods, they are ephemeral containers. Any input data needs to be fetched from outside, like cloud storage, database, when the job starts. And critically, any results or output must be written back to persistent external storage before the job finishes and the pod disappears. Nothing inside the container lasts.
Got it. Use the job API, make it idempotent, treat the container as temporary. What about specific configurations for these job or cron job objects?
Right, the spec has some important fields. For a basic job, you can tune things like parallelism. If your task can be broken down into chunks, you can set parallelism to run, say, 5 pods concurrently, each processing a part of the work. Completions works with parallelism. It tells the job how many of those parallel pods need to finish successfully for the whole job to be considered complete. Active deadline seconds is super useful. It's a hard time limit for the entire job. If it runs longer than this, OpenShift will kill it, prevents runaway jobs from consuming resources forever, and back-off limit controls how many times Kubernetes will retry a pod within that job if it fails, exits with non-zero status, before marking the whole job as failed.
Okay, those are for one-off jobs. What about scheduled cron jobs?
For cron job scheduling, the key field is schedule, obviously. You set that using standard cron syntax, 5 for every 5 minutes, etc. Concurrency policy is important. What happens if a job takes longer than its schedule interval? Forbid, the safest usually, means a new job won't start if the previous one is still running. Replace means the old one gets killed and the new one starts. Allow, the default, lets them potentially run in parallel, which needs careful thought about idempotence. Starting deadline seconds gives some slack if the cluster is busy. How long after the scheduled time is the job still allowed to start? And then you have successful jobs history limit and failed jobs history limit. These are just cleanup settings. How many old completed or failed job and pod objects should OpenShift keep around? Good to set these low, like 1 or 3, to avoid clutter.
Still need resource requests and limits, I assume?
Absolutely. Resource management applies just as much. Set requests and limits for your job containers. It helps the scheduler place them, prevents them from starving other workloads. You might even give lower priority batch jobs, lower resource requests, so they tend to get scheduled during off-peak times when there's spare capacity.
Makes sense. And how do they signal they're done? How does startup completion work?
The main thing is the exit code. The primary process in your job container must exit with status code 0 on success. Any non-zero exit code signals failure to Kubernetes, potentially triggering retries based on that backoff limit. If you need setup steps like downloading data or credentials, you can use init containers. They run to completion before the main job container starts. And yes, graceful termination with sigterm still matters. If the system needs to stop the pod while it's running, maybe the node is draining, the job should ideally catch sigterm and try to clean up or save state if possible before exiting.
Okay. Now, scaling and updates for jobs sound different. You don't have a service running all the time.
Exactly. Scaling batch jobs isn't about having more pods running continuously. It's usually about increasing the parallelism for a single execution of the job, using that parallelism field we talked about. If you need to process more data, you might launch the job with parallelism, 10 instead of parallelism. 5. Another pattern is a work queue. You might have a queue of tasks and you run multiple identical worker pods, maybe managed by a job with high parallelism, or even a deployment if the workers are long running, that just pull tasks from the queue until it's empty.
And updates. How do you roll out a new version of a batch job?
You don't really update a running job instance. Updating batch jobs means you build a new container image with your changes. Then you either run a new job using that new image, or for a cron job, you update the cron job definition, the YAML, to point to the new image tag. The next time the schedule triggers, it will launch pods using the updated image. If you have a long-running job that needs fixing midway, you'd typically cancel or delete the old job and start a fresh one with the corrected image.
So CI/CD is about building the image and applying the updated job or cron job definition.
Precisely. Your pipeline builds the image, using immutable tags, of course, pushes it, and then applies the updated Kubernetes YAML for the job or cron job resource.
Got it. Last piece for jobs. Observability. Seems tricky since the pods vanish afterward.
You nailed the challenge.
Yeah.
Observability relies heavily on logs precisely because the pods are transient. Logging to stout stater is absolutely critical. If those logs don't get shipped off the node by the cluster logging agent before the pod is deleted, they are gone forever. And if your job produces tangible results like a report file or process data, make double sure it writes that output to persistent storage before it exits. Don't rely on finding results buried in log messages.
What about metrics? Less common.
Metrics are less common for short jobs, yeah. Standard Prometheus scraping doesn't work well for things that aren't running long. If you do need metrics, like number of records processed, you might have the job push those metrics to a Prometheus push gateway just before it exits, or maybe it updates counters in an external database. Notifications are often really useful for batch jobs, though. Set up something to send an alert, Slack, email, when a critical job completes successfully, or especially if it fails.
Okay, that clarifies jobs nicely.
Yeah.
They definitely have their own set of good citizen rules focused on that run-to-completion model.
Yep. Different workload, different considerations.
Right. Now, for the final category, and often the one that causes the most head-scratching, stateful applications. We're talking databases, maybe message queues that hold persistent data, applications that need stable network names to find each other. Why are these inherently trickier on OpenShift?
They're tricky because they fundamentally break that core assumption of statelessness. The idea that any pod is disposable and identical. Stateful apps have, well, state. They rely on data that must survive pod restarts or rescheduling. Or they need a stable, predictable network identity so peers or clients can reliably connect to a specific instance. Managing that kind of persistent state and identity in a dynamic environment like OpenShift requires special handling.
So you definitely can't just chuck a database into a standard deployment object and hope for the best.
Please don't. That's asking for trouble. The first principle is use the right tools. Primarily, that means stateful sets or operators. Kubernetes stateful sets are specifically designed for this. They provide two key things that deployments don't. One, stable, unique network identifiers for each pod, like mydb0.myservice, mydb1.myservice. And two, stable persistent storage. Each pod in a stateful set gets its own persistent volume claim that follows it, even if it gets rescheduled to a different node.
Okay, stateful sets handle the basics. What about operators?
For more complex stateful systems, especially things like cluster databases, Postgres, MySQL, Cassandra, etc., operators are often the way to go. An operator is essentially automation of human operational knowledge. It's a custom controller running in your cluster that understands how to manage a specific application, how to properly configure it, scale it, handle backups, manage upgrades, react to failures, do failovers, all the complex lifecycle stuff. If there's a well-regarded operator for your database, it's usually worth using.
So use stateful sets, or even better, an operator if one exists. What else? Storage seems key.
Absolutely critical. Second principle, you must use persistent storage via persistent volume claims, PVCs. The stateful set defines a template for PVCs, and OpenShift ensures each pod gets its own unique persistent volume based on that template. You need to choose a storage class that actually meets the performance, reliability, and access mode, like read-write once, only one pod mounts it at a time, requirements of your stateful application. The source explicitly warns don't try running a high-throughput database on slow, basic NFS storage, for example. That can lead to terrible performance or even data corruption.
Right. Match the storage to the workload.
Yeah.
And identity.
Stateful sets provide that consistent identity. Pods get those predictable names, pod 0, pod 1, and there's usually a headless service created too, which gives stable DNS records for each pod individually. This is crucial for clustered applications where pods need to discover and talk to specific peers.
And don't treat them like pets.
Yeah, try to avoid that. Even though they have state, you still want to manage them through OpenShift as much as possible. Use init containers for setup, rely on the platform to handle rescheduling, avoid SS lading and tinkering manually if you can help it.
Okay, what are the really critical configuration points that are unique to stateful apps?
Well, persistent volume claims are foundational, as we said. Define the template in the stateful set, make sure the storage class is right, monitor the volume usage. Health probes need extra careful tuning. Readiness probes are still important to know when the app, for example, the database, is fully up and ready to serve requests after potentially long startup or recovery. But liveness probes, you need to be cautious. You really want to avoid restarting a stateful pod unnecessarily. Imagine a database is doing some heavy internal work, maybe checkpointing or handling a complex query, and it becomes briefly unresponsive. Restarting it via a trigger-happy liveness probe could force a lengthy crash recovery process, which is often much worse than just waiting a bit longer.
So make the liveness probes less sensitive. Longer timeouts, higher failure thresholds.
Exactly. Increase failure threshold, maybe increase the check period seconds, definitely use a sensible initial delay seconds. You might even consider if a liveness probe is appropriate at all for some very stateful components, relying more on readiness and external monitoring, which leads directly into graceful startup and shutdown, even more vital here and often needing more time. On startup, a database might need minutes to replay logs or sync with peers. Readiness probes need to account for that. You might use specific startup probes, which have their own longer timeouts just for the initial start sequence. And shutdown.
Oh boy.
The application must handle SIGTERM cleanly. It needs to flush all its in-memory data to the persistent disk, close connections, maybe coordinate with cluster peers. The default 30-second termination grace period seconds is often not enough for a busy database to shut down cleanly. You absolutely need to check your application's requirements and likely increase this value significantly in the stateful set spec, maybe to 120 seconds, 300 seconds, whatever it needs.
Because if you don't,
If you don't give it enough time and it gets sig-killed, you risk data corruption, inconsistent state, and long, painful recovery times when the pod restarts. It's probably one of the most common ways people shoot themselves in the foot running stateful workloads on Kubernetes.
Yikes. Okay, increase that grace period. What about config and services?
Configuration and secrets are still managed via ConfigMaps and secrets, though updating them might require more care if it involves, say, a database schema change that needs coordination. Service and endpoint management. Stateful sets get that headless service for peer discovery. If clients need a single stable entry point, like always talking to the current primary leader database, you might need an additional regular cluster IP service. How that service targets the correct pod, the leader, often needs dynamic updates, which is something operators frequently handle automatically. Clients also need to be smart enough to handle disconnections and reconnect, possibly to a different instance if a failover occurs.
That graceful shutdown needing more time feels like a really critical takeaway. What happens if someone misses that, uses the default 30 seconds on a busy database, and initiates an update?
That's a classic bad citizen scenario leading to problems. The rolling update starts. OpenShift picks pod DB0, sends its sig term. The database starts its shutdown flushing caches, writing buffers to disk, maybe releasing locks, but it's busy. It takes, say, 90 seconds. After 30 seconds, OpenShift's default grace period expires. It assumes the app is stuck and sends sig kill. Bang! Power pulled. The database process crashes, potentially leaving its data files inconsistent. Now, the stateful set tries to start DB0 again, maybe on the same node or a different one, attaching the same persistent volume. The database process starts, sees the inconsistent files, and has to initiate crash recovery. This might involve replaying transaction logs, which can take a long time, consume lots of I/O and CPU, and meanwhile that instance is unavailable. If this happens sequentially to each pod in a cluster during a rolling update, you could end up with significant downtime or performance degradation. Just increasing termination grace period seconds avoids all that pain.
Okay, message received loud and clear on shutdown. So how do scaling and updates work with these stateful constraints?
Yeah, replicas and scaling are usually much more deliberate. Unlike stateless apps, you typically cannot just use an HPA to automatically scale a traditional database cluster up and down based on load. Many stateful systems have fixed topologies or require complex procedures to add or remove nodes, like data rebalancing. So avoid uncontrolled autoscaling. Scaling a stateful set, changing the replicas count, is usually a manual planned operation. Or if you're using an operator, the operator might provide a custom way to trigger scaling that includes all the necessary application level steps. You really need to understand how your specific application handles scaling.
So no HPA on my Postgres cluster.
Generally, no. Not on the primary stateful set itself, maybe on read replicas if they are managed separately and are more stateless-like, but not on the core stateful components. Rolling updates with stateful sets work, but carefully. By default, ordered ready policy, they update pods one at a time, in order, pod n, then n1, down to 0, or 0 up to n1, depending on the strategy. It waits for one pod to be fully updated and ready before starting the next. A pod disruption budget, PDB, is still very relevant. For a 3-node cluster, you might set min available, 2 to ensure quorum is maintained during updates. For a single instance stateful app, replicas, 1, a PDB with min available. 1 effectively tells OpenShift, don't voluntarily evict this pod during maintenance, and admin needs to handle it manually, which can be desirable for critical singletons. And crucially, version compatibility. When you roll out a new image version, it must be compatible with the existing data format and potentially able to interoperate with older versions still running during the update. Database schema migrations often require careful planning, sometimes needing multi-stage updates or manual steps. Always test upgrades thoroughly in staging. If using an operator, follow its specific upgrade documentation to the letter.
Right, updates are possible, but much more involved. Okay, final round for stateful. CI/CD and observability.
CI/CD for stateful apps needs that extra care. Pipelines still build images, immutable tags, maybe deploy manifests via GitOps, but automated testing becomes more critical. You should test data migration scripts, maybe spin up temporary database copies to validate upgrades. Deployments might be less frequent and more carefully managed than for stateless services. Backups and data management. This is huge. OpenShift does not automatically back up the data in your persistent volumes. Let me repeat that. You lose that PV, your data is gone unless you backed her up. You must have a strategy. Use tools designed for Kubernetes backups, maybe OpenShift's own data foundation features if you use that storage, or tools like Valero or vendor-specific database backup tools that integrate with cloud storage. And please, please test your restores regularly. A backup you haven't tested restoring is just hope, not a recovery plan.
Solid advice. Logging, Metrics.
Logging is still stat starter. Be mindful that databases can be very chatty. Configure log levels appropriately and ensure your cluster logging stack can handle the volume. Correlation IDs are still useful if requests flow through the stateful service. Metrics are arguably even more critical for stateful apps than stateless ones because you can't just scale them out easily. You need insight into performance and capacity. Use specific exporters, like PostgreSQL exporter, Redis exporter, to get detailed metrics into OpenShift monitoring Prometheus. Track things like query performance, cache hit rates, disk I/O, replication lag, disk space usage. These metrics inform capacity planning, tuning, and troubleshooting. Tracing. Less common to trace inside the database itself, but definitely trace the application calls to the stateful service. Knowing how long interactions with the database or cache take is vital for understanding overall request latency.
That's a really thorough breakdown. Stateful apps definitely earn their advanced reputation. Understanding storage, identity lifecycle, and using the right tools like stateful sets and operators is key to making them good citizens.
It takes more planning, for sure, but it's definitely achievable.
Okay, so we've looked deep into the specifics for stateless, batch, and stateful workloads. But hanging over all of this, there must be some general rules, best practices that apply to any application you want to run well on OpenShift.
Yeah, absolutely. Think of these as the universal principles of being a good OpenShift citizen, regardless of what your application actually does.
Let's run through those then. What are the big ones?
First, we've touched on it, but it bears repeating. Externalize configuration. Never ever hard code environment-specific settings like database passwords, API endpoints, or feature flags directly into your container image. Use ConfigMaps for plain configuration and secrets for anything sensitive. Inject them into your pods using environment variables or mounted files. This makes your image portable across dev, staging, prod you build once, deploy anywhere, just changing the external config. It's fundamental for security and manageability.
Makes sense. Build once, configure per environment. What's next?
Service discovery. Your applications need to find each other. Don't hard-code IP addresses or node host names. That's brittle and breaks constantly in a dynamic environment. Always use Kubernetes services. A service provides a stable internal DNS name, like http://my-namespace.svc.cluster.local.808h. Your application code should connect using these service DNS names. OpenShift ensures the name always resolves to healthy pods backing that service, handling load balancing automatically.
Okay, use service DNS names internally. How about getting traffic in?
For external access, use routes and ingress. OpenShift routes, or standard Kubernetes ingress resources, are the way to expose your internal services to the outside world. They provide external host names, handle TLS termination so your app might not need to deal with certificates, and route traffic to the correct backend service. Make sure you secure your routes properly, use TLS, maybe add authentication via OAuth proxy or restrict access by IP if needed.
Right, and how does the application identify itself within the cluster?
That's where service accounts come in. By default, pods run with a default service account in their namespace, which might have more permissions than necessary. Best practice is to create dedicated service accounts for your different applications or components. Then, use Kubernetes role-based access control, RBAC, roles and role bindings, to grant that specific service account only the minimum permissions it actually needs to do its job. Like, maybe it only needs to get ConfigMaps in its own namespace, nothing else. Principle of least privilege.
And you can even tighten that further.
Yeah, if your application code never needs to talk to the Kubernetes API server itself, you can set auto-mount service account token, false, either on the pod spec or the service account itself. This prevents the Kubernetes API token from even being mounted into the pod, reducing the attack surface if the pod were compromised.
Security keeps popping up. Seems like a core theme of being a good citizen. What other security practices are generally recommended?
Oh, definitely. Security is woven throughout. A huge one is run as non-root. Your container image should be built so the application process inside does not require root privileges. Why? Because OpenShift's default security policies, security context constraints, or SCCs, are designed to prevent containers running as root by default. The standard restricted SCC assigns an arbitrary, random, non-root user ID when the container starts. Your application must be able to handle this. Usually it just means ensuring the process itself doesn't need root, and any directories it needs to write to inside the container are group writable, often group ID 0, which the arbitrary user ID belongs to. Running as non-root massively limits what an attacker can do if they compromise your container.
So design the Docker file and app permissions correctly from the start.
Exactly. And related to that, understand security context constraints. SCCs. Stick with the default restricted SCC whenever humanly possible. It prevents privileged operations, mounting host directories, and other risky things. Only request a more permissive SCC, like Inuit or privileged, if you have an extremely compelling, unavoidable reason and understand the risks. Make sure your image works within the constraints of restricted. Then there's least privilege in code. Don't open unnecessary network ports in your container. Don't include libraries or tools you don't actually need. Use minimal base images, like Red Hat's UBI Minimal or Alpine, to shrink the potential attack surface. You can also explicitly drop Linux capabilities your process doesn't need using the security context in your pod definition.
Keep the image small and tight. What about the images themselves?
Image trust and management. Use base images from trusted sources that are regularly updated, like Red Hat UBI or official language images. Rebuild your application images frequently to pick up security patches in the base image and dependencies. Integrate image scanning tools like Claire, Trivy, or scanners built into registries like Quay into your CI/CD pipeline to catch known vulnerabilities before they get deployed.
And we talked about tags before.
Yes, worth repeating. Immutable tags. Use unique version tags for production images. Don't reuse tags like v1.0 for different builds. Use commit hashes or build IDs. This ensures reproducibility and reliable rollbacks. Image streams in OpenShift help manage the promotion of these specific trusted tags through your environments.
Okay. What about network security between pods?
Network policies. This is a big one. By default in Kubernetes and OpenShift, network connectivity is wide open. Any pod can talk to any other pod across namespaces, usually. Network policies let you define firewall rules at the pod level. You can say things like, pods with label app frontend can only talk to pods with label app backend on port 8080, or pods in namespace A cannot talk to namespace B at all. A common best practice is to apply a default deny policy to a namespace, blocking all incoming traffic, and then explicitly allow only the necessary connections. This dramatically limits the blast radius if one component is compromised, crucial for defense in depth.
Right. Lock down the network traffic. Anything else on security?
Just reinforcing access control and secrets. Use RBAC properly to control who, users, and service accounts can do what in which project's namespaces. And keep sensitive stuff like passwords, API keys, certificates, and secret objects, not in ConfigMaps, not hard-coded, not in Git. Secrets are stored encrypted at rest in OpenShift backend, etc. Remember to have a plan for rotating secrets periodically, too.
That's a solid set of security principles. Any other general best practices that wrap things up?
Just a couple more general points from the source. Try to stick to the one process per container model. Your main container should run your primary application process. If you need helper utilities or agents, consider running them as separate sidecar containers within the same pod. Avoid running, say, a web server and a database inside the same container image. It complicates management, scaling, and resource allocation. Design for the pod lifecycle. Assume your pod can be stopped and restarted at any time. Handle SIG-term gracefully. Make your initialization logic idempotent so restarting doesn't cause issues. Ensure your app can robustly reconnect to dependencies if they become temporarily unavailable. Be mindful of resource quotas and limits that might be applied at the namespace project level by cluster admins. And consider using the vertical pod autoscaler, VPA, maybe just in recommendation mode initially, to get suggestions for tuning your pod's CPU and memory requests based on its actual historical usage. Monitoring and alerts should cover everything. Use OpenShift Monitoring Prometheus to scrape metrics from all your workloads stateless, batch, stateful. Set up meaningful alerts using Alert Manager and custom Prometheus rule objects for things like high error rates, latency spikes, resource saturation, job failures, pods stuck in crash loops. Good citizens make it easy for operators to know when something's wrong. And finally, for more complex setups, especially with lots of microservices, consider service mesh, like OpenShift Service Mesh, which is based on Istio. It can provide powerful features like automatic mutual TLS between services, sophisticated traffic control, canary releases, A/B testing, fault injection, circuit breaking, and enhanced observability, metrics, tracing, often without you needing to change your application code. It pushes those cross-cutting concerns down into the platform infrastructure layer. So yeah. If you follow these general guidelines, plus the specific ones for your workload type, your applications become much more reliable, secure, easier to manage, and truly integrated with the OpenShift platform. They become good citizens.
Wow. Okay. That was definitely a deep dive. We've gone all the way from stateless basics through batch jobs, tackled the beast of stateful apps, and covered those really crucial general practices. It's so clear that being a good citizen on OpenShift isn't just about writing code that works in isolation. It's about designing and configuring it to actively cooperate with that dynamic orchestrated environment.
Absolutely. It's about architecting your applications for the platform so you can actually leverage its strengths. Things like the automatic scaling, the self-healing, the built-in security features, the smooth updates. It saves so much manual effort and just makes things more stable in the long run.
It really hammers home how thinking about where your application runs is just as vital as thinking about what it does.
Which leads to a really interesting question for you, our listener, to think about. Looking at an application you're dealing with now, or maybe one you're planning, which one of these good citizen practices we discussed feels like the most important one it's currently missing? And maybe flip that around. Which one seems like it would be the biggest challenge to actually implement in your context, and what makes it challenging?
Definitely some good food for thought there. Thanks for joining us on this deep dive.